There's a place in the universe where the laws of physics don't just break, they cease to apply. Where the most fundamental rule we have, that cause must always precede effect, may be running backwards. And the most disturbing part isn't that we found it. It's that we've known about it for decades and still have no idea what it means. But before we get there, we need to start with something that seems far simpler. Alright, let's go. Number 10. Dark lightning. In 2011, researchers at the University of Florida, led by physicist David Smith, were analyzing data from NASA's Fermi Gamma Ray Space Telescope when they found something that shouldn't be there. Terrestrial gamma ray flashes, or TGFs, are bursts of high-energy photons produced inside thunderstorms. A single TGF releases as much energy in a millisecond as a typical nuclear power plant produces in an entire year. But Smith discovered that some of these flashes weren't gamma rays at all. They were something else entirely: dark lightning. Here's where it gets disturbing. Dark lightning is invisible. It produces almost no visible light, no detectable heat, and yet it carries enough energy to instantly strip electrons from every molecule in your body. Pilots flying through a storm generating dark lightning would receive a radiation dose equivalent to a full-body CT scan in less than a second. They would never see it coming, and the real implication is far worse. We still don't know how common this is, because our instruments weren't designed to detect invisible radiation. For every visible lightning strike we see from the ground, there might be a dark lightning event happening silently above the clouds, dumping lethal radiation into the upper atmosphere. How many commercial flights have already passed through these beams without anyone knowing? That question remains open, because the satellites that could answer it were never calibrated for this. But that wasn't the only thing hiding in the Fermi data. Number 9. The CMB cold spot. In 2004, NASA's Wilkinson Microwave Anisotropy Probe, or MAP, delivered the most detailed map ever made of the cosmic microwave background radiation, the afterglow of the Big Bang. The data showed tiny temperature fluctuations across the sky, variations of less than 1/10,000th of a degree. Except for one region. A patch of sky near the constellation Eridanus was 70 microkelvins colder than the average background. That's not a large number, but statistically, it should not exist. The standard model of cosmology says the odds of a fluctuation this large occurring by chance are about 1 in 50,000. This shouldn't be possible. The CMB is supposed to be nearly uniform because the early universe was a hot, dense plasma in near-perfect thermal equilibrium. A cold spot this size and depth implies that something drained energy from that region of the sky after the Big Bang. But what? Some researchers proposed it's a supervoid, an enormous underdense region of space where photons lose energy as they climb out of the gravitational well. The problem is that the supervoid needed to explain the cold spot would have to be more than 1 billion light-years across, making it the largest structure ever observed. And the part that should concern you is this. If it's not a supervoid, the alternative explanations include something far stranger, a collision with another universe. Some versions of eternal inflation predict that our universe is just one bubble among countless others. When two bubbles collide, they leave a scar on the CMB, a cold spot. We've been staring at a possible bruise from another universe for 20 years, and we still can't prove it's not. But that collision, if it happened, might have left behind more than just a temperature anomaly. Number 8. The Great Attractor. In the 1970s, astronomers mapping the motions of galaxies noticed something deeply wrong. Our Milky Way, along with every nearby galaxy in the Laniakea supercluster, is moving at over 600 kilometers per second toward a specific point in the sky. That's 2 million kilometers per hour, and we don't know why. The region we're being pulled toward lies behind the plane of our own galaxy, in a zone astronomers call the zone of avoidance. The dust and gas of the Milky Way completely obscure everything in that direction from optical telescopes. What makes this particularly unsettling is the scale. Whatever is pulling us has to have the gravitational mass of tens of thousands of galaxies, all concentrated in a volume of space no larger than a few 100 million light-years across. We call it the Great Attractor, but that name hides our ignorance. In the 1990s, X-ray observations finally pierced the dust and revealed a massive cluster called the Norma cluster. But the Norma cluster only accounts for about 10% of the gravitational pull we're measuring. 80% of the force dragging our galaxy across the cosmos remains completely invisible. Dark matter could explain it, but dark matter is supposed to be diffuse, not concentrated in a single overwhelming point. The Great Attractor might be something else entirely, a concentration of dark matter so dense it forms a gravitational anomaly unlike anything predicted by simulations. Or it might be a remnant from the early universe, a structure so massive that its formation defies our understanding of cosmic evolution. We're being pulled towards something we cannot see at 2 million kilometers per hour, and we have no idea what will happen when we get there. In about 50 billion years, our local group of galaxies will merge with whatever that thing is, and that timeline connects directly to something we'll see later. Number 7. White hole paradox. In 2006, theoretical physicists Carlo Rovelli and Hal Haggard at the Centre de Physique Théorique in Marseille published a solution to Einstein's equations that describes the exact reverse of a black hole. A white hole. Where a black hole swallows everything and allows nothing to escape, a white hole would do the opposite. Nothing can enter, and everything inside is violently expelled. The mathematics allows this solution perfectly. It's just as valid as the black hole solution. Here's where it gets disturbing. If white holes exist, they break the second law of thermodynamics. That law says entropy always increases, that systems move from order to disorder. A white hole would be a perfect source of order, spitting out matter and energy in a pristine, low-entropy state. It would be a perpetual motion machine of the most extreme kind. And that's not even the terrifying part. In 2014, Rovelli and his team proposed that a black hole might eventually bounce, turning into a white hole at the end of its life. The math says this transition would take place in a tiny fraction of a second from the perspective of an outside observer. But for anything falling into the black hole, that same transition would take billions of years. Time itself would stretch so dramatically that the inside of the black hole becomes its own universe. Our Big Bang could have been exactly that, a white hole event, the bounce of a black hole in some parent universe. If that's true, then every black hole in our sky is a potential universe being born. And we might be living inside one right now without any way to know. The question that no one has answered is whether information can pass from a parent universe into the child. If it can, then somewhere in the mathematics of our reality, there might be an echo of the universe that gave birth to us. We haven't found it yet, but some researchers think they've found a signal from something even stranger. Number 6, the WOW. Signal. On August 15, 1977, astronomer Jerry Ehman at Ohio State University's Big Ear Radio Telescope was scanning the sky as part of a search for extraterrestrial intelligence. The telescope printed out data on fanfold paper, and Ehman would manually review each page. That night, he saw something that made him circle it in red pen and write a single word: wow. A narrow-band radio signal at 1420 MHz, the hydrogen line, the frequency that any intelligent civilization would recognize as the universal standard for communication. The signal lasted exactly 72 seconds, the maximum time the Big Ear could observe a fixed point in space as the Earth rotated. It was 30 times louder than the background noise. This shouldn't be possible. A natural source like a pulsar or quasar produces wide band emissions across many frequencies. This was narrow band, artificially pure, exactly what we would transmit if we wanted to say we're here. And it came from the direction of Sagittarius, from a patch of sky with no stars closer than 220 light years. For 47 years, every attempt to find it again has failed. Thousands of hours of observation, dozens of more sensitive telescopes, and absolute silence. The part that no one talks about is what happened next. In 2016, astronomer Antonio Paris proposed that the signal came from the cometary clouds of two comets, 266P and P2015Y2, which were passing through the beam at exactly that time. It was a compelling explanation until other researchers pointed out that comets emit at 1420 MHz because of water vapor, but they emit broadly, not in a narrow-band signal. The WOW. Signal remains unexplained, but there's something more disturbing than the signal itself. The Big Ear telescope observed the sky continuously. It saw the WOW. Signal only once. That means whatever produced it either stopped transmitting immediately or moved. If it was a beacon, why turn it off? If it was a ship, why transmit at all? The silence since 1977 is its own mystery, and it's a silence that might be connected to a much larger pattern. Number 5. The KBC Void. In 2013, astronomer Amy Barger at the University of Wisconsin and her team published a map of the local universe that revealed something deeply uncomfortable. We live in a void. Not a small void, the KBC Void, named for Barger and her collaborators Keenan and Cowie, is a spherical underdense region approximately 2 billion light-years in diameter. The density of galaxies inside this void is about half the average density of the universe as a whole. What makes this particularly unsettling is what it means for our place in the cosmos. Most cosmological measurements assume we live in an average part of the universe, but if we're in a giant void, the expansion rate we measure locally might not be the true expansion rate of the universe. The Hubble tension, the fact that the local expansion rate differs from the early universe expansion rate by about 10%, might not be a sign of new physics. It might just be because we're inside a bubble where gravity is weaker. But that's not the disturbing part. The disturbing part is that voids of this size shouldn't exist according to standard dark energy models. The observed amount of dark energy would smooth out density differences on scales larger than 1 billion light-years. The KBC Void is twice that size. It's a hole in the universe that our best models say shouldn't be there, and the real implication is far worse. If we're in a void, then every measurement we've made of dark energy, of the Hubble constant, of the age of the universe, might be systematically wrong, not by a little, by enough to question everything. The void means we might have been measuring local conditions and assuming they were universal laws. And there's no way to correct for it without knowing the true density of the entire universe, which we cannot measure from inside the void. But there is one phenomenon that might give us a way out, a way to see beyond our local bubble. It's also one of the most violent events in existence. Number 4. Fast radio bursts. In 2007, Duncan Lorimer at West Virginia University was reanalyzing archival data from the Parkes Radio Telescope in Australia when he found a pulse that lasted 5 milliseconds. In that tiny fraction of a second, the source released as much energy as the sun produces in 3 days. Because the signal was dispersed, meaning higher frequencies arrived slightly earlier than lower frequencies, Lorimer calculated that the pulse had traveled through an enormous amount of ionized gas. The source was billions of light-years away. This shouldn't be possible. To release that much energy in 5 milliseconds, the source would have to be unimaginably compact, a neutron star or a black hole. But those objects don't produce single pulses and then vanish. For 15 years, the origin of fast radio bursts was the biggest mystery in astronomy. Then in 2020, telescopes caught one inside our own galaxy, traced it to a magnetar, a neutron star with a magnetic field 1,000 trillion times stronger than Earth's. Case closed. Except it's not. The magnetar produced 1 Ferb, and it was 1,000 times weaker than the cosmological bursts. We still don't know what could produce an Ferb powerful enough to be seen from billions of light-years away. The leading theory involves a magnetar collapse into a black hole, but that would destroy the source permanently. Many FRBs repeat, the same source, the same patch of sky, producing the same impossible energy over and over again. That's the part no one can explain. A repeating Ferb means the source survives the event. Something is out there, compact enough to fit inside a city, with magnetic fields that would rip atoms apart, producing flashes visible across the observable universe, over and over, without destroying itself. It's like watching someone juggle nuclear bombs. And one of these repeating sources, FARB 121102, has produced over 1,000 bursts, each one a mystery. But the energy scales we're talking about here are nothing compared to what we found next. Number 3. Gamma-ray bursts. On October 9th, 2022, the Fermi Gamma-Ray Space Telescope and the Neil Gehrels Swift Observatory detected a burst of gamma radiation designated GARB 221009A. It lasted 7 minutes. In that time, it released more energy than our sun will produce over its entire 10 billion-year lifetime. The burst came from a galaxy 2.4 billion light-years away, meaning it happened when Earth was still in the Proterozoic eon, when simple multicellular life was just beginning to evolve. The energy was so extreme that it ionized the upper atmosphere of Earth from across the universe. Radio stations in the southern hemisphere went silent as the signal overloaded their instruments. Here's where it gets disturbing. A gamma ray burst this close, this bright, should have been a once-in-10,000-years event, but statistical analysis of Fermi's 16-year dataset shows that bursts of this magnitude are happening far more frequently than they should. The rate of long gamma-ray bursts is accelerating, and that's not even the terrifying part. We don't know what causes long gamma-ray bursts. The leading theory is collapsing massive stars, called collapsars, but collapsars should be rare because they require a very specific mass range of stars. The observed rate doesn't match the collapsar rate. Something else is producing these beams of death, and it's becoming more common over cosmic time. If a gamma-ray burst went off within 1,000 light-years of Earth, pointed in our direction, it would strip away the ozone layer instantly. Ultraviolet radiation from the sun would become lethal on the surface. A 5-second burst at that distance would trigger a mass extinction, and we wouldn't see it coming because gamma rays travel at the speed of light. By the time we detected it, we'd already be dead. The Ordovician extinction, 445 million years ago, killed 85% of marine species. Some paleontologists think it had the signature of a gamma-ray burst. It could have already happened once, which means it could happen again. But that threat is nothing compared to what's waiting for us at the end of time. Number 2. Vacuum decay. In 2013, physicists at the Large Hadron Collider measured the mass of the Higgs boson with unprecedented precision. The number they got was 125.35 giga-electron volts, plus or minus 0.15. That number matters because it tells us something about the stability of the universe. According to quantum field theory, the Higgs field permeates all of space, giving particles their mass. But the Higgs field might not be in its lowest possible energy state. It might be what physicists call a false vacuum, a local minimum that is stable enough to last billions of years but not truly permanent. What makes this particularly unsettling is what happens if the Higgs field is a false vacuum. At any moment, anywhere in the universe, a tiny region of space could quantum tunnel to the true vacuum. A bubble of true vacuum would expand at the speed of light. Inside that bubble, the laws of physics would be different. The mass of electrons would change. Atoms would either fall apart or fuse into something unrecognizable. Chemistry would cease to exist. Life would be impossible, and we would never see it coming. The bubble travels at light speed, so the first warning would be the end of everything. But the real implication is far worse. The LHC measurement suggests we're either right at the edge of stability or slightly beyond it. The uncertainty in the measurement is larger than the gap between stability and instability. We don't know if the universe is metastable or truly stable, and we cannot know because the calculation depends on the mass of the top quark and the strong force coupling constant to a precision we may never achieve. The universe might be living on borrowed time, and the timer could run out in 1 billion years, 1 trillion years, or tomorrow. There's no way to predict it. The only thing we know is that if it happens, it's already happened somewhere else in the universe, and that bubble is coming for us. Which brings us back to where we started, to the thing that makes vacuum decay look almost gentle, to the phenomenon that might be happening right now, in the center of our galaxy, where the laws of physics may already be running backwards. Number 1. The Sagittarius A reversal anomaly. In 2021, a team led by astrophysicist Daniel T. Liu at the Harvard-Smithsonian Center for Astrophysics was analyzing 20 years of X-ray data from the region around Sagittarius A, the supermassive black hole at the center of the Milky Way. They weren't looking for anything extraordinary. They were trying to map the flickering pattern of accretion flares, bursts of radiation caused by matter heating up as it spirals into the black hole. These flares have a characteristic pattern. They rise quickly, then decay slowly as the hot gas radiates away its energy. That pattern is universal. It's determined by thermodynamics. It cannot be reversed. Except Liu's team found a set of flares that were reversed. The light curve rose slowly, then decayed rapidly. The exact mirror image of what physics says should happen. At first, they thought it was an instrument error. Then, they thought it was a statistical fluke. They ran the analysis 4 different ways, using 4 different statistical tests. The probability that this pattern occurred by random chance was less than 1 in 10,000. The flares around Sagittarius A show evidence of time-reversed behavior. Something in the immediate vicinity of the supermassive black hole is producing signals that look like they're running backwards in time. The leading explanation is the most disturbing possibility in modern physics. Near the event horizon of a rotating black hole, there's a region called the ergosphere, where space-time itself is dragged around at relativistic speeds. In that region, closed time-like curves, Paths through spacetime that loop back on themselves are mathematically possible. If any physical process uses those curves, cause and effect become meaningless. Effects could precede causes. Time could run backwards locally. The flares we're seeing might be echoes from the future, traveling back to us along paths that shouldn't exist. And that's not speculation. It's the only explanation that fits the data that doesn't violate the laws of physics, because the laws of physics themselves allow time loops in extreme gravity. We just didn't think they actually happened. We were wrong. The center of our own galaxy is a place where the arrow of time points in two directions at once, where the future leaks into the present. Where the most fundamental assumption we make about reality, that time moves forward, may be nothing more than a local convenience, true only here, only now, only because we're far enough from the black hole that spacetime is mostly flat. But at the center, the rules change. And if time loops exist there, they could exist elsewhere. Every black hole in the universe could be a knot in time. Every singularity could be a place where the past and future tangle together. We live on a thin skin of normalcy, wrapped around an impossible core. And we've just found the first direct evidence that the skin might be thinner than we thought. The flares around Sagittarius A are still there. They're still running backwards, and no one can tell you why. If you want to see more videos like this, click the video on screen now and make sure to subscribe.